Hello everyone, welcome to Vishesh Educational Videos. In this video, I am explaining homogeneous coordinates, one of the important topics in computer graphics. So let me begin with the explanation of homogeneous coordinates. So before understanding homogeneous coordinates, you need to understand what is a transformation first. So if you want more information related to different types of 2D transformations, you can refer my video. The link is in the description section, right? So here I am going to give very little details that is necessary for understanding the homogeneous coordinates. So transformation is nothing but it's a manipulation that can be applied on objects, right? So here you should know one thing: transformation can be applied on objects. So my object can be triangle, rectangle, pentagon, or etc. Whatever the object you take, you can apply the transformation for that object. So transformation means you can manipulate the object, right? So manipulation means you can move your object from one position to another position, or you can increase the size or decrease the size of your object, or you can rotate the object in clockwise or anti-clockwise direction, right? So this is the transformation. Now, what are the different types of transformations? There are three types I am considering here: translation, rotation, scaling. So translation means you can move your object from one position to the other position. Rotation means you can rotate your object with respect to particular angle, right? Either you can rotate in clockwise direction or you can rotate in anti-clockwise direction. Scaling means you can increase the size of the object or you can decrease the size of the object. So it's very simple. Here you can observe that my object is transformed from one form to another form when you move it, when you rotate it, or when you increase the size of it, right? So you can go through my video 2D transformations, right? Now these are the matrix forms for these three translations. The first one is, this is the matrix form for translation. Here tx and ty are translation parameters, x dash and y dash are the new values. New values, how you are going to get means by adding the old values plus translation parameters. Remember one thing, in translation you are going to use addition operator, right? This is the scaling matrix form. In scaling you can see here you are using a multiplication operator, and in rotation also you can see there you are using a multiplication operator, right? So in translation you are going to use addition operator. In rotation and scaling you are going to use multiplication operator. This is very important, remember that. Here you can see here scaling x dash y dash, this is the old values, x dash y dash, these are the new values, x and y old values, sx and sy are the scaling parameters. Here you can see here p dash is equal to s into p. Here translation can be given as p dash is equal to t into p. P dash is equal to t into p. Here scaling p dash is equal to s into p. This is the rotation. Remember one thing, this is the rotation of anti-clockwise direction. By default, if you don't specify the direction of rotation, it will take anti-clockwise direction, right? So that's why this is the matrix form for anti-clockwise direction. You can see there p dash is the new point after rotation, p is the old point before rotation, r is the particular rotation value, right? So getting, guys? So these are the three different matrix forms. Here you have to remember one thing. Here you can observe here this matrices, all these matrices are 2 into 2 matrices. 2 into 2 matrices means 2 rows and 2 columns. You can see any matrix you can see here. So here see 2 rows, 2 columns, 2 rows, 2 columns, 2 rows, 2 columns. So remember that here the matrix forms for translation transformations such as translation, scaling, rotation, all the matrix forms are 2 by 2 matrices. Now so see here, so this is one way to represent the matrix forms for different transformations. You can represent these matrices in different way also, that is possible. So this is another way of representing the transformations, right, in a matrix format, right? This this is also right, but you can represent in another way also. See here, so whatever the transformation you take, you can represent that transformation in the form p dash is equal to m1 into p plus m2. This is the general matrix format. You can use this general matrix for all the three different types of transformations, either translation, rotation and scaling, right? I will show you. But before that, matrix M1, this M1, what it is? It's a 2 by 2 matrix containing multiplicative factors. Now M2, this is the, it is also two-dimensional column matrix, but it contains translation parameters. Which one? M2 contains translation parameters, M1 contains multiplicative factors. Getting, guys? Remember one thing, if you are representing a rotation and scaling, which matrix you need? You need M1, because M1 contains multiplicative factors. You know that rotation and scaling use multiplication operator. That's why you can represent rotation and scaling using M1 matrix. In the same way, translation use addition operator, right? That's why translation use M2 matrix. Getting, guys? Getting? And one more important thing, M1 is the identity matrix. Identity matrix means all the diagonal values will be 1. I will explain why it is in the coming slides, but just remember M1 is the identity matrix, that means the diagonal the diagonal values will be 1. Getting, guys? So this is the general format. I can represent my rotation or a translation or scaling by using this general format only. Yes, I can do that. See how it is. I can make some changes and I can represent my different transformations in the same equation, same general format. See, so this is the, this is the general format, right? Matrix representation format. P dash is equal to M1 into P plus M2, right? This is the general format. Now you can see, for rotation, for scaling and for translation, I used the same general format, but I did slight changes to represent different transformations. You can see here, M1 contains multiplicative factors. That's why I told you M1 matrix is used by rotation and scaling, because they use multiplication operators. In the same way, M2 contains translation terms. That's why M2 matrix is used by translation transformation, right? And one more important thing, what I told, M1 is the identity matrix. That means just remember that this matrix value is 1. Don't get confused. The matrix value, the values that are present in the identity matrix will be equal to 1. Just remember that. Now see, for rotation, I can write the equation as P dash is equal to R into P plus 0. So here you can see here R into P. M1 is replaced with R because M1 contains multiplicative factors, right? That's why I can replace that matrix. I can replace the contents, rotation contents. So I did that. Into P, it is same old point, but M2 is 0. Why M2 is 0? I told you M2 is used for only the translation. That's why I made it 0. See, this is the general equation only, but I altered it for rotation. In the same way for scaling, P dash is equal to S into P plus 0. You know that S is nothing but scaling parameters. That's why M1 contains rotation and scaling parameters here. That's why M1 contains are replaced by scaling parameters. P is same word point, no problem. But again here also M2 matrix is 0 because M2 is only for translation. Now for translation you can see here P dash is equal to P. P dash is equal to P. Here you can see there M2 contains translation parameters. That's why I used M2. See, but you can ask a question, M1, what happens to M1? I told you M1 is the identity matrix. That's why 1 into P is what? P only. So that's why P dash is equal to P plus T. So getting, guys, I take this general matrix format, general matrix representation, and I can convert that matrix, general matrix representation into different transformations as I want. Right? Now, so one thing, so what is homogeneous coordinates here? Why we need this? First of all, what is homogeneous coordinates? Why we need homogeneous coordinates? When we apply composite transformations, we need homogeneous coordinates. Getting, guys? So when we need homogeneous coordinates, when we apply composite transformations, we need homogeneous coordinates. Now you can ask a question, then what is a composite transformation? Composite transformation means series of transformation applied to a single object. Right? Composite transformation means series of transformations applied to a single object. See, this is the example for a composite transformation. So, right, this is the square object here. For this object, right, for the single object, I'm applying two transformations here. I'm applying scaling also, I'm applying translation also. Getting, guys? For a same object, I'm using two different transformations. For a same object, square, I applied scaling first. That means I increased the size of the object. Next, after scaling, I applied transformation to the object square. This is the second transformation. For the same object, for the single object square, I applied two different transformations, scaling and translation. So this is the final output. The final output you got after applying two transformations, scaling and translation. So this is composite transformation. So composite transformation means you can apply, right, two or more transformations to a same object, right. Now, but to use composite transformation, to apply composite transformation to an object, I need to convert 2 by 2 matrix into a 3 by 3 matrix. You can see here, you can see here all my matrices in the translation, scaling and rotation, all my matrices are 2 by 2 matrices only. I can't use this 2 by 2 matrices for composite transformation. That's why I need to convert my 2 by 2 matrices, into 3 by 3 matrices. Now, how you are going to convert 2 by 2 matrices into a 3 by 3 matrix means, right, to convert 2 by 2 matrix into 3 by 3 matrix, I need homogeneous coordinates. Getting, guys? So now you understood, right? Why I need homogeneous coordinates? To convert 2 by 2 matrix into 3 by 3 matrix. To apply the composite transformation, I need 3 by 3 matrices only. I don't need 2 by 2 matrices because I can't use 2 by 2 matrices for composite transformations. That's why I will convert that using homogeneous coordinates. See. So what is that then? So in simple words, I will tell you, a homogeneous coordinate technique means what you are going to do means you are going to represent your coordinate information. For example, here how many coordinates you are seeing? 2 coordinates, x, y coordinates for a particular right object, right? So you can represent this x comma y coordinate, right, as xh comma yh comma h. Here how many right elements were there? 2 elements were there, but here this is a 3 element representation. How I am going to represent this? xh comma yh comma h. Here the h is there, right? H. So h is nothing but a homogeneous coordinate. I will take the example, you will understand that. So far you have seen that, right? So I converted my 2 coordinate form into 3 coordinate form because you know that 2 by 2 matrices you can't use. That's why I have to convert into 3 by 3 matrices. That's why I need to convert my coordinate values to xh, yh, h. H is nothing but a homogeneous coordinates here. And remember, h is a non-zero value. H is a non-zero value. So we will see this. See, so x is equal to xh by h, y is equal to yh by h. Don't get confused, guys. Here, suppose, see, I will explain this. Suppose my coordinate value is what? X comma y. You know that I told you, right? This is two element format. Now I have to convert it into 3 element format, right? How I am going to do means homogeneous for x comma y comma h. Homogeneous form x comma y comma h. I included h. Now what I consider? Yeah, what is the value I consider for h? 1. I consider the value for h as 1. Why? See, x by h, y by h. Any value that is divided by 1, the value remains the same, right? You can divide any value by 1, the value won't change. That's why I am considering h value as 1. Even if your h value is multiplied or it's divided, no problem, the value remains the same, right? But it is converted into 3 element format. Getting, guys? You can use this format x comma y comma h for any coordinate value, no problem, because the h value is what? 1 only, right? See, x, for example, I will consider x as 2, y as 3. 2 by 1, 2 only. 3 by 1, 3 only. Nothing will change. That's why I can use this h, because this is value, the value of h is 1. So to represent my x comma y into x comma y comma h. Getting, guys? Now you can see here, this is the homogeneous coordinate for translation, right? I am converting my 2 by 2 translation matrix into 3 by 3. So you can see this 2 by 2 matrix, that is x dash y dash is equal to xy plus tx ty. So I am converting this. See, x dash 1 0 tx, y dash 0 1 ty, 1 0 0 1 1. Now you can ask a question, sir, this format is completely changed. No, this format is not at all changed. See, I will do the matrix multiplication here. See, 1 into x, x. You know that, right? Matrix multiplication, left to right, top to bottom. See the highlighter, 1 into x, x. 0 into y, 0. Tx into 1, tx. So here, what are the values you got? X, tx. So x dash is equal to x tx. See now, x dash is equal to x tx. Value won't change. See, in the same way, y dash k, y dash, see here, 0 into x, 0, 1 into y, ty into 1, ty. So y ty, y dash is equal to y ty. See, value won't change. Getting, guys? So 1 0 0 1, this thing remains the same. For x dash y dash also 1 is there, for xy also 1 is there. Obviously I used 1 in both the sides, no problem. Getting, guys? So even if I converted the matrix format into homogeneous form, the values won't be affected. So this translation operation can be written as p dash is equal to t of tx comma ty into p. You can see here this tx comma ty. This is the 3 into 3 translation matrix. You can see. Right, guys? In the same way, I can use two-dimensional rotation transformation equations. See, this can be represented. See here, x dash y dash, same thing. See, rotation cos theta minus sin theta cos theta, cos theta minus sin theta cos theta. See, cos theta minus sin theta cos theta. Getting, guys? Just see here, this is the format 0 0 1 0 0 1. If you do matrix multiplication, you can see that the value won't change here. See, so this is written as p dash is equal to r of theta into p. Here r of theta is 3 by 3 matrix. This is here, this is right, guys. Next, in the same way, scaling x dash y dash 1 is equal to sx sy 1. See, this is the scaling, right? Scaling transformation. This is the three-dimensional scaling matrix. See here, the scaling operator sx comma sy. This one. P dash is equal to s of sx comma sy into p, right? This sx comma xy is this one matrix. This is a 3 into 3 matrix with parameters sx and sy. So getting, guys? So homogeneous coordinates means, in a simple words, you can convert two-dimensional matrix into 2 into 2 matrix, that is two-dimensional matrix into three-dimensional matrix. Why? Means mainly to apply composite transformations, right? So in this video I'm explaining inverse transformations also. You can see here. So what is inverse transformation? Inverse means reverse. For example, you see here, if you are moving the point in the rightwards direction, that is, if you are moving the point from left to right, then the inverse of that is right to left. In the same way, if you are rotating the object in the counterclockwise, then inverse of it is clockwise. If you are scaling the object to increase the size, then the inverse of it is decreasing the size. Inverse means reverse, opposite, right? So opposite matrix formats, right? So these are see here, I will explain this. For translation, we can obtain the inverse matrix by negating the translation distances. Simple. To convert your translation means translation value into negative. For example, I told you, you are moving from left to right means now you have to move from right to left. Then what you should do? Just simple, you should negate that values. See, minus tx minus ty, t of inverse, inverse of translation. Same matrix only. See, guys, same matrix only. Inverse means reverse, right? Opposite, right? That's why instead of plus value, I am using minus value here. Minus tx minus ty. See? Simple. I should negate it. That's all. In inverse rotation, I told you, by default what rotation it will take means anti-clockwise direction. But opposite means, reverse means, now this is the matrix format for clockwise direction. Getting, guys? So cos theta minus sin theta was there See, cos theta minus sin theta was there in which one? Counterclockwise, that is anti-clockwise, that is default. But here you can see cos theta sin theta is there, the negative sign is moved here, reverse. That is, this matrix is for clockwise direction. Earlier one was for anti-clockwise. This matrix is for clockwise direction. Getting, guys? R inverse. This is T inverse. Now, we form the inverse matrix for a scaling transformation by replacing the scaling parameter with the reciprocals. You can see here. Sx can be replaced by 1 by Sx. Sy can be replaced by 1 by Sy. Right? You can see. The scaling parameters are replaced by these reciprocals. Sx is replaced by 1 by Sx. Sy is replaced by 1 by Sy. Getting, guys? So S inverse is this. Same matrix only, you can see. See? Same matrix. But for example, think that this is to increase the size. Definitely this will be to decrease the size. Opposite. Inverse. 1 by Sx, 1 by Sy. Reciprocals you have to use. Right, guys? Hope you understood the concepts. If you have any doubts, please post your doubts in the below comment section. Thank you. Thank you for watching the video.